So do the resistive network. So you can just write R1 and so the input node you can write V in, and then the output node is V out, let's say, and decided to do 1K, and then the cap is V out to, and you can write the capital word GND, which is a global for ground, and that should be 1 pico. And what I would do is first do a dot global GND and dot end, so that way your main one is taken care of, and then dot control dot end C. So this is where the control is going to go. Okay. So your RC network is done, and then you put the voltage sources. And like I said, if your node name is V in, try to avoid the source being V in as well. So just write VS1 or something like that. DC voltage you can write. Okay, so we haven't used a pulse source yet. Okay, so you can start with a pulse source. Now, there are two ways you can search for them. One is you just go to the manual directly, right? So I have the manual up here somewhere. Yeah. So, and just type Control F and pulse. If you don't know pulse, then, you can search on the web. But here we know if you search pulse, it comes as directly over here. So you don't have to go to Perplexity or Notebook or Google to find out. And so just use the pulse source over here. And that's the format. So wherever you give the voltage source, you remember the first one is your DC value. And after that, we had given AC1. And here we're not going to do any AC simulation, so you don't have to give that. We'll just give a DC value, and then we'll give the pulse. Okay. And the pulse, the syntax is this. Let me just zoom out a little bit. So this is a syntax. So V1 means the lower voltage, V2 is the higher voltage, and you can actually swap them. You can have this higher voltage, lower voltage. It just change the phase, obviously. And then the delay. So it'll remain the lower voltage till you get to the delay, and then the pulsing will start. TR is rise time. Okay, fall is fall time of the pulse. Pulse width, period, NP. I don't know what is NP. You can ignore that actually, but a number of pulses. So okay, I mean typically in most simulators actually this doesn't exist. This is a nice one. So basically what this means is you can have a non-periodic pulse and then do number of pulses and you'll just keep repeating it. But here we'll do periodic, so it'll just, you don't have to worry about this one. Okay. So that's it. And everything is in seconds and volts and amperes. So I think this everyone is aware of. So let's do that with V sine. So you'll pulse. Sorry. So so your command is going to be some name of the voltage source. Like I said, name it other than the node name. You don't have to, but it is always good. So that way you don't get into trouble later on. Positive node, which is V in, ground, DC voltage 0 is fine. And then we'll write pulse. Pulse 0 to 5. Delay, I'll just give 1 nanosecond just so that, it doesn't start with like a falling wave. Then what's T rise, T fall? You can keep it really sharp, like 1 picosecond. You might get into convergence issues. Sometimes you can't do that, but here it should be fine. And then T rise, T fall, pulse width, period. Okay. So we are doing 1 K, 1 pico. What's tau? Hmm? The RC, but what's the number? See, 1 pico is 10 to the power minus 12. That'll be 1 picosecond if you had 1 ohms. This is 1,000 times more. So 1 nanosecond. Okay, 10 to the power 1 nanosecond. So if I have tau as 1 nanosecond, and let's say you know that 5 tau, it kind of settles to almost the value. So at least the pulse width needs to be 5 tau, but let's do 10 tau. So that way we know it's fully settled. Okay. So 10 tau means 10 nanoseconds should be the pulse width, and the period will do it twice of that because we want the rise and the fall will be same. So the period will be 20, pulse width will be 10. Okay. So let's do 10 nano pulse width, 20 nano period, and that number of pulses you can ignore. Okay, got it? So this circuit, you don't have to do a OP, but it's always a good idea to do it. So let's first do a operating point, and then let's do a transient simulation. And so each period is 20 nanosecond. We'll do like maybe 2 cycles, okay, so that we get to charging and dischargings. So you do 2 cycles, 20 times 2 is 40 nanoseconds. So we'll simulate it for 40 nanosecond, and it's always a good idea to make the time step like 1,000 times lower than that. So in transient, if you remember, the first one is the time step, and the second one is the period of time you're trying to simulate. So we'll simulate it for 40 nanoseconds, and time step we'll keep it 1,000. This is when we deal with convergence and all that. It's more important. Just keep it 40 picosecond, okay? Or you can do 10 picosecond, 10 picosecond and 40 nanosecond is what we are going to simulate it for. Okay. Everyone's got it? So just get this going and we'll simulate first, plot and make sure it looks right, and then we'll try to measure it. Okay. Hmm? That's also always a DC value. So that is mandatory. You cannot skip that. Okay. Before 0, actually it is mandatory in almost every simulator. I don't know in Ngspice. Okay, but then put it. See, the DC operating point, you should always have a DC voltage. Okay. It probably takes this as the DC voltage, but put that value. Okay, that DC value. So then when you're doing operating point, you're sure that that's the value. Yeah, like in Xspice and Spectre, you have to actually put that value, but maybe here it's not necessary. But DC value, always put it. That's a good habit to be in. So everyone has how many of you have the net list now, the complete net list? Okay, so maybe we can keep going and the rest of you just try to catch up. All right, so here you can just command line, you can type ngspice that. So in my case, I have named it as MES trans. So we'll run it. Okay, so if everything is run, no error, you'll get this V in, V out, and the branch voltage. So it's all 0 because the DC value is 0. Now let's plot V out and see how it looks like. So plot V of V out. Okay, so looks like, it is behaving the way we want. So this is 10 nanosecond, 5 tau is almost half of it, and this is half of it, so 5 nanosecond. And you can measure it right here. So why don't you go ahead and measure it on the plot itself? So we want to start from, what is it? 0.45, right? Roughly 0.45 somewhere here, all the way to 4.5. Okay, so we had calculated what, 2.2. So you can see it's 2.26 nanoseconds. Okay, rise that 10 to 90. That's because, I'm just like eyeballing, but we'll calculate exactly using measure statements. This is just to see, this is always a good way to quickly check, like, are you in the ballpark? If something is totally off, at least here you know that you haven't made any, major errors. So if you calculate the 10 to 90, it shows 2.26. Let's do the 90 to 10. So if you do 90 to 10, so it'll be roughly somewhere around here. So that comes out to be 2.45. Again, that's just my mouse action is not good. Now let's do 20 to 80. So 20 is what? 1 volt to 80, 1 to 4, right? So 1 to 4, 1 to 4 is 1.38. We calculated 1.32, again 1.3, then it's close. Okay. And then if you do 4 to 1, that's 1.5 because again my mouse error. Okay. So looks like the circuit is kind of working the way we want. Okay. So I'll allow you guys to, simulate, measure it with the mouse, and then I'll show you how to do that with measure statement. Or what you can do is start looking into the manual and figure out how to do measurement. Okay. Or the other way you can do is, maybe this is a good time to try. Uh, so if you have Perplexity Pro or Google Notebook, you can create a space. So I already have a space with that. So you can see that I actually added the manual in the Perplexity space. So that way, when you ask question, it will try to get it from the manual, and then just ask it like, hey, I want to measure rise time, fall time, Ngspice, but I would say put the manual, you'll get some better result, and put the manual in, or just try it like that, or try Google, try the manual itself. We'll see what we get. So it'll be the same measure statements now, but because this is transient, the syntax will be slightly different, but the same kind of principle like what you did for AC simulation. So how many of you are done with all the 4 rise fall and all the 2 rise delay and fall delays? Okay, good. So you can now start finding out the pulse width and the period of the output wave. Period. And you calculate that by taking the output 50% to 50%, pulse width from 50% to 50%. Okay. So I'm going to just overlay here itself. It's exaggerated it, but so this is a little crowded one, but so delay is input 50 to output 50, delay rise, input 50 to output 50, delay fall. And then the pulse width is 50% of the output rising to 50% of the falling. That's pulse width. And the period is from rising 50% of 1 to rising 50% of rise 2. This is where you're going to use the rise 1, rise 2. You got it? Yeah. Well, if it is like perfectly, if it is a fast rising one, then it doesn't matter where you do it, it'll be the same. But since this is a slow one, so 50% is usually what you will take. Because see, if you take 90%, any small error on the top will get magnified. Because that's where yeah, 50-50. Again, this is not something which is like, it's like a theory, but depends on the application, but that's typically what you would do. Fall, yeah. So typically, pulse width is what is the time you're on for. Okay, so that's what you're. Yeah. No, no, no. It should come the pulse width which you have given, right? The other one should be from the fall, not from the rise. But how can it be zero? The first one you get is the 50% of the rise. Second one is the 50% of the fall. And that should be exactly equal to 20 nanoseconds, right? No, yeah, ln of this thing, but the second one is the ln of fall, which is after 20 nanosecond, right? It's not at the same 20 nanosecond. Yes. Okay. Able to do it. So all measurements done. All right. So good. So when we come back, we'll take a short break. When we come back, maybe 10 minutes break. Come back, what I'll show you how to now do it in variables. Okay. Because what you have done so far, that's hard coded. Now, if I say, oh, change the VDD from 5 volts to 3 volts, then this whole thing will collapse, right? It will not work because you have done everything hard coded. So we'll change. So we'll copy this file. We'll keep this one, copy this file and do it as parameters and variables and do that. Okay. 10. Yeah, it's whatever you have chosen because the rise time and the fall is same here. So it should be same. Okay. Okay, by the way, I just forwarded something on the group. So we are doing this pilot program with this AI company. They're trying to do attendance and quizzes using their AI algorithm. So we decided to do the pilot